Hi everyone, welcome to my new video in the Mathematics Essentials series. In this video we are going to cover some properties of radicals. Actually I'll only do one property of radicals so that I can keep the video shorter than some of the previous ones. But I'll do a few videos on properties of radicals. In the previous video I did say that this video would be on surds, but when we are simplifying expressions that involve surds, we end up using some properties of radicals. So I figured I should cover those first, and if I'm going to cover them, I might as well prove them so that you know why they are true. So, without further ado, actually a sip of coffee is due. Okay, I'm good. All right, without further ado, the product property of radicals, that's the name of the property that I'm going to show you in this video and prove. The product property of radicals. I'm going to assume that you know what radicals are. And I'm going to assume that you understand why we cannot take the square root of a negative real number and get a real number answer. Okay, so if you're unfamiliar with these facts, a quick Google search will remedy this. But if you would like to post a question in the comments about any of that, feel free and I will get back to you. Okay, now let's state the product property of radicals. What is it? Well, for any pair of real numbers, let's just call them A and B. So for A and B in the real numbers, as long as they are non-negative, in other words, greater than or equal to 0, okay, because 0 is not positive or negative. Okay, if we had said, for instance, that A and B are strictly greater than 0, then we would know that they are positive. Okay, that would mean that A and B are positive. But because we're allowing for the case where they could be 0, all we know is that they are not negative. In other words, non-negative. Okay, so for A and B in the reals, where they're both non-negative, if you know that these preconditions hold, then it turns out that this also holds. The square root of A times the square root of B equals the square root of the product of A and B. Okay, now, if you're familiar with the product property of radicals, you will know that it doesn't just hold for square roots. Okay, so these are like square roots. You don't have to write the 2 for square root, but really this holds for any root. So the nth root of A, whatever n happens to be, times the nth root of B would just equal the nth root of A times B. Okay, but to keep this proof easier to look at, I'm just going to prove it for square roots. All right, and if you're concerned that I'm not proving it for general roots, so for the nth root, where n is just some arbitrary real number, well, all you would have to do is go through my proof, and everywhere where there is a square root, take an nth root instead, and everywhere where there is a square, raise it to the power of an n instead. Okay, so don't sweat it that I'm not proving it for nth roots. All you would have to do is change all of the square roots and all of the squares to nth roots and powers of n respectively, and the proof is just structurally identical. Okay, so in order to prove this, I'm going to make use of a property of powers and exponents. Okay, and if you're not familiar with this property, you will be in 30 seconds. Okay, and if you're worried that I haven't proved it, don't worry, because there will be a video on powers or exponents or indices. They all mean the same thing later in this series, and then I'll prove these properties when I'm covering that topic. But for any two real numbers, x and y, okay, if you were to raise them to the nth power, you know, for example, if you were to square them, then that would just be the same thing as raising them individually to the nth power before multiplying those results together. So it doesn't matter whether you just multiplied the real numbers first and then raise them to that power, or if you raise them both to that power and then multiplied those results together. Okay, you're going to get the same answer. It's going to come down to the same thing in the end. So this property here I'll just write a green star. Okay, so because when I'm doing the proof, I can just write a green star to show you where that property applies in the proof for the product property of radicals. So let's prove the product property of radicals. I'll show it to you again. For any real numbers, a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, in other words, they're both non-negative, then the square root of a times the square root of b is just going to be the product of a and b and taking the square root. Okay, so it doesn't matter whether you found the square root of a and you found the square root of b individually, multiplied those results, you could have just as well multiplied a and b and then taken the square root of the result of that product. Okay, let's go ahead and prove it. Proof. Now, to proceed with this proof, what I have to do is assume all of these preconditions in this top line to be true. And if you are not used to mathematical proofs, it might seem a bit strange that sometimes you can just assume something to be the case in a proof. You can't just assume what you want, but you can't just assume whatever you want. But and you certainly cannot assume the thing that you're trying to prove. But in some cases, you are at liberty to make assumptions in proofs, and in fact, you have to. So why is that? Why can I assume everything, all of the preconditions in this top line to be true? In fact, I must. Why is that the case? Well, think about what the product property of radicals is saying. It's not saying that everything in this top line is true or that everything in this bottom line is true. Okay, what it is saying is that a scenario in which these conditions happened to be true, then what's said here in the second line would logically follow. So you're being asked to show that the second line logically follows from a scenario in which the conditions in the top line are true. So the product property of radicals doesn't say anything about when these conditions are false. Okay? All right? So that's why we can assume what's in the top line. And depending on what level of mathematics you're doing, if you're watching this video, then this probably applies to you. Your teachers will probably expect you to write out this assumption, all right? But in later mathematics, typically it's known that the author of the proof would have to assume these preconditions to be true. So, you know, if they're writing for perhaps an audience that has more experience with mathematics, often they might leave those assumed preconditions unstated because readers would just know that someone would have to assume them to even get started with the proof, okay? But in earlier mathematics, it's a very good habit to write out all of your assumptions, especially if it's on an assignment rather than an exam, because in an assignment you have more time to solve the problems. You know, maybe you have a week or 2 weeks to do an assignment. So I will write out the assumptions, okay? So suppose, this is me making my assumptions explicit, that A and B are real numbers and they're both non-negative. Okay, then consider the square root of A times the square root of B. Well, once we assume these conditions, all right, that means that it makes sense to assume that the square root of A is going to equal something, okay, because it's not negative. All right, so if you take the square root of a real number, so long as it's not negative, it's going to have an answer. So the square root of A must equal something. And similarly for the square root of B, it must equal something. Okay, now this isn't part of the proof, but it's just to tease out my reasoning. Suppose that the square root of A just equaled X and the square root of B just equaled Y, then we'd be multiplying them together. And we couldn't multiply two real numbers and fail to get a real number. Okay, their product would have to equal some other real number Z. Okay, so it totally makes sense to know, you know, to just know that the square root of A times the square root of B is going to equal some real number, okay? Which is why we are at liberty to introduce some notation. We can say that the square root of A times the square root of B equals C. I'm just going to pick C, okay? Where C is a real number, because we know that about C as well. We don't know what the square root of A times the square root of B equals, but we know it's going to be some real number, and we are just calling that C. Okay, now consider what happens if we were to square both sides of the equation. So we'd have to put the left-hand side of the equation in brackets because we're squaring everything on the left-hand side. We're also squaring everything on the right-hand side We have to do that to keep the equation balanced, but that's just going to be c squared. Okay, now what I'm going to do is apply this property here, which I've indicated with the green star. Okay, so you can think of the x here as the square root of a, and the y here as the square root of b, and that whole left-hand side is just being raised to the nth power, which in our case is 2. Okay, so I have this kind of case on the left-hand side of my proof, and I'm going to rewrite the left-hand side like this. Okay, so that property allows me to do that. So you can think of the square root of a being raised to the second power, so I'll put it in brackets, okay, times the square root of b being raised to the second power. Don't really need that dot in the middle. Okay, and the right-hand side is just going to remain c squared. There's not really much we can do on the right-hand side. But now notice that this square here, would undo this square root, okay? And similarly for the square root of b squared. So the squares will kill off the square roots. What the red arrow points to will kill what the purple arrow points to. Okay, so the square will kill the square root, but it's a self-sacrificing mission because the squares will die in the process. Okay, so in other words, we can just drop the squares and the square root on the left-hand side, and we would be left with just a times b. Okay, because there'd be no need for the brackets either, right? Okay, just a times b. We could write the brackets, wouldn't be wrong, but we don't need them. Okay, and on the right-hand side, we'll just be left with c squared still. But now we can take the square root of both sides of this equation. So on the right-hand side, we'll be left with the square root of c squared. And since we took the square root on the right-hand side, we have to take it on the left-hand side as well. So we'll be left with the square root of the product of a and b on the left-hand side. Now, just like before on the left-hand side, we can see now on the right-hand side, the square root will undo the square, okay? So square roots undo squares, and squares undo square roots, because they are inverse operations. That's what it means to undo each other. They're inverse operations. Okay, so on the right-hand side, we'll just be left with c. And on the left-hand side, there's nothing really we can do. It's just the square root of a times b still. But now, notice what's happened. We started off... Actually, I'll show you this first. Remember what the product property of radicals said. It said that the square root of a times the square root of b was equal to the square root of the product of a and b. Okay, and what we said, okay, I'm going to keep the same colors, we said that the square root of a and b was equal to c. But, what color did I use? I used green. Okay, but we also found that the square root of the product of a and b was equal to c. So, what this means is that what's underlined in red, if what's underlined in red is equal to c, and if what's underlined in green is equal to c, then what's underlined in red must be the same thing as what's underlined in green. Okay, so the kind of reasoning at play here, okay, is that, if you had, for instance, if you knew that x was equal to z, but you knew that y was equal to z as well, well then you'd know, these two facts together would imply that x equals z, okay? The fancy way, the mathematical, or the formal logic way of saying this is that the equality relation is transitive, okay? That's not how you write, this here is not how you express transitivity, but I don't want to express transitivity, I just want to make things clear and obvious. Sorry, you'd know that x is equal to z, but you know that x is equal to y. Okay, sorry, typo. All right, so yeah, this here is not how you would express transitivity, but I don't want to focus on transitivity. I just want to tease out the intuition about what's going on with the red, the green, and underlines and the blue arrows pointing to C. Okay, so often you would not be expected to write this out in your proof, but if you're doing a first year mathematics course at university, or perhaps a senior mathematics course in high school, you'd probably be expected to write something like this. Since the square root of a times the square root of b equals c, and the square root of the product of A and B equals C. The square root of A times the square root of B is equal to the square root of A times B. Oop. Yeah, so you might not have to write that out, but maybe you should just to be safe. In an assignment, you should probably write it out. Okay, so that's everything that we needed to show, which means we have earned the right to write this square off to the right-hand side here, which means that we have proved what we set out to prove. Okay, so this property, this one indicated by the green star here, that, okay, we applied that in this line of the proof. Okay, so that's the product property of radicals proven for you. There's another property of radicals called the quotient property of radicals. That's for the next video. Often a mathematics textbook will mention the product property of radicals and the quotient property of radicals. But some textbooks will mention a third property, and I kind of don't like that it gets treated as a third property. But since some textbooks do it, I should show it to you. And I'll explain why I don't really like it being treated as a third property. So this property is this. It doesn't really get a name, and you can tell I'm biased, nor should it, but you'll see why. Perhaps you'll agree with me. That if you've got two real numbers, actually it's not even two real numbers, like for any real number, A, as long as it's greater than or equal to 0, the following holds. That the square root of A times the square root of A just equals A. Okay? Now, I'll show you why this is not really a third property. So we've got the product property of radicals, which I've proven, and the quotient property of radicals, which I'll show you in the next video. And then we've got this seemingly third property. Well, remember, the product property of radicals, I'll just show it to you again, in case you don't recall it, but it says that the square root of A times the square root of B is equal to the square root of the product of A and B, so long as A and B are real numbers and they're both non-negative, right? Well, this here is just a special case of the product property of radicals. And what's special about this case? It's that A and B happen to be equal to each other. So to make this more obvious, okay, what do we get when we simplify this? Square root of A times the square root of A. Well, we would get, just like the product property says, square root of A times A, which would just be the square root of A squared. And then the square root would undo the square, and we would get A. Okay, but to make this even more clear, let's write it in terms of A and B. Well, the product, so long as A and B are real numbers and they're both greater than or equal to 0, this would be equal to the square root of the product of A and B. All right, but what if it turned out that B just happened to equal A? Okay, well then, this would just be the square root of A times A. Okay, if A equals B, we'd be just as much justified in saying the square root of B times B. Okay, and this would be the square root, because A times A is A squared, so it'd be the square root of A squared, and that would equal A. Or if you like B more than A, this would be the square root of B squared, and that would just equal B. So this isn't really a third property, okay? It's just a special case of the product property of radicals. Anyways, if anything in this video was not clear, please drop me a comment. There are no silly questions, okay? If there are any, chances are I've asked it myself before, okay? So the product property of radicals for A and B in the reals, where they're both non-negative, the square root of A times the square root of B is equal to the square root of A times B. We use this property of exponents or powers or indices, whatever you want to call them, written in green, in our proof. All right, and that's where we used it. I'll prove that property in some other video. And then we made use of a kind of inference like this, okay, to conclude that this thing here must be equal to that thing here, and that's exactly what the product property of radicals said. Then we looked at this supposed third property that often gets a mention in textbooks, and we realized that it's not really a third property after all, because it's just a special case of the product property of radicals where A and B happen to be equal. Okay, so if you found this video helpful, feel free to give it a like or share it with some friends. And if you'd like a notification for when I release a new video, feel free to subscribe. Until next time, bye for now.